everyone. Let's start talking about some trig derivatives. Um, to start off with, there's a couple of special derivatives or limits that we use to reduce some of our more difficult problems. You could prove these using squeeze theorem. There's tons of videos out there about these two. If I have time, I'll do it in class, but for now, let's just talk about them. The first one is if you look at the limit as x approaches 0 of sine x over x, first of all, if I were to plug in a 0, I would get 0 over 0, which means there's a hole, and I can reduce it out. And so this does end up going to 1. This does have to be as the angle approaches 0, or as x approaches 0. Same thing on the bottom, x approaches 0, but this time it's 1 minus cos x over x. And again, if I plugged in a 0, I'd get 1 minus 1, or 0 over 0. So that's a hole. My graph actually does approach 0. So these two guys are important. So I'm going to use this first one on the next page, and I want you to look at, it's going to be written a little differently. So um, for this particular relationship, and I'm going to put this off to the side, if I do the limit as x approaches 0, and I have something like sine of 5x over 5x, as long as these two positions are the same, you still have that relationship of it going to 1. So if we can make those two arguments match, then and it is as it approaches 0, then we can say all of that is 1. So that's something we're going to work on this first example. So the problem, of course, is that the bottom isn't 5x, it's 2x. So we're going to do some things to convert that. So the easiest thing to do is multiply by something that will give me a 5x. Now I can get real specific here, but the easiest way is probably just to multiply by 5. But whatever you do to the bottom, you have to do to the top. So then look what I'm going to do. I'm going to split this up into, I'm going to bring that 5 out front. And this 5 on the bottom, this is all multiplication. So I'm going to just group the 5 and the x together. Now, hopefully you guys can see this part right here is what I'm looking for, right? So I can even think of it as bringing that 5 halves out front if I really want to. I could have also left it inside. So I really have this. This part is 1. This is still multiplication. So I still get 5 halves is my final answer. Here we've got the limit as x approaches 0 of tan of x over 2x. Again, if I plug in 0, tan of 0 is 0. 2 times 0 is 0, so there must be something I can do. So my first suggestion when you're dealing with trig is to maybe rewrite them. So I'm actually going to split this up a little different than you guys might think. I'm going to split it up like this. That also helps you guys kind of understand what I'm doing a little bit better. Tangent is really sine over cos. Okay. And then I'm going to do one more grouping issue. I'm going to think of it, well, I guess I can do it like this. I'm going to think of it like this, but I'm actually going to be grouping just that little piece together. And since it's multiplication, I am allowed to do this. So I'm going to separate this into the limit of sine x over x times the limit of what's left over. This is because I can do that. That's a rule of limits. So then what's left over is 1 over 2 cos x. Make sure that you're okay with what I just did there. Okay, this part's 1, and this part, when I plug in a 0, careful, cos of 0 isn't 0, it's 1. So I really get times 1 over 2 times 1, or 1 over 2, so 1 half. All right, and this last one, I'm going to split this up, and some of you guys your favorites are not fractions, let's put it that way. So I need to make sure that you understand something about fractions. If I have multiple pieces in my numerator, I'm allowed to split those up and divide them by the denominator, separately. I'm going to do that here because, again, if I plug in 0 for x, I'm going to get 2, I'm going to get 0 plus 1 minus 1, which is a 0 on top over 0. Again, when I get 0 over 0, there's something I can do. In this particular case, that something is splitting them up like I did here. So I'm going to split this into 2x over 3x, 1 over 3x, and minus cos x over 3x. And then I'm going to attack each of them separately. So I can reduce if I want to, so I'm going to reduce that. And then I'm going to do the limit of just 2/3 plus, and then actually I'm going to choose to put these back together. You're going to see why in 1 second. So I'm going to choose to make this limit as x approaches 0 of 1 minus cos x over 3x. Some of you might already be seeing or remembering where we just saw that. This guy is easy. Limit as x approaches 0, there is no x to plug in, which means it's just 2/3. Here, just that portion, if you recall, the limit as x approaches 0 of 1 minus cos over x is 0. Now, there technically is a 3 on the bottom, so there really was a 1/3 times that, but because that was a 0, that just ends up being 0. So you just get 2/3 in general. That might take a couple of times through to really get comfortable with. Okay, now we're going to move into our the actual derivatives of our trig function. So, like the derivative of sine is cos, or the derivative of cos is, careful, negative sine. There's some interesting things here with squares and negatives and some products. So you do need to memorize these and know these. If you don't want to memorize them, you can make them happen. If you remember, the derivative in general is this guy, right? This is the definition. I'll do the first one. If I was doing the first one, my function would be sine x. So this would be the limit as h approaches 0 of sine of x plus h minus sine of x over h. Now this is trapped in here. This is not, you can't distribute the sine. It doesn't work like that. But you did learn in pre-calculus that if you have the sum inside or you're adding angles inside, you can split that up using this relationship. Sine of the first angle, cos of the second angle, plus cos of the first angle, sine of the second angle. That's all this expanded. And then, of course, I still have the minus sine x. I am not going to ask you to do this. That's why we're learning these. You could even get some flashcards, but I want to show you where this comes from. Okay, so then I'm going to group these two guys together. Why? Because they both have a sine x, and that seems like something I could factor out. So I'm going to take the sine x. If I take sine x out of this guy, I get cos h. If I take sine x out of that, I get minus 1. And this is all still over the denominator. So I'm going to group those together. And then I have this guy left. And so that term is just cos x sine h over h. Okay, maybe you're starting to see where this is going. This guy, if I looked at that, that's very close to 1 minus cos of h over h, which we know is an identity that we just talked about in a few slides, but I'd have to factor out a negative 1. So that's what I would do here technically, bring a negative 1 out front, and then this, as you recall, just goes to 0. So this whole part is going to go to 0. This guy should also look familiar. That part, as h approaches 0, is 1. So I get cos of x times 1. So all of this reduces down to cos x. Woo! That was a lot of work just to go from here to here. That's why we're letting you use these trig derivative rules. So there's a lot of work that you don't have to do because you're just learning this. So by learning this, you're saving yourself a lot of time. You're welcome to do this whenever, but my tests aren't really made up for you to do that every time. Okay, so let's try one. And I pasted some of the rules down here that we're going to use later. So first of all, we're not quite ready to tackle this. There's a couple of ways that we can solve this guy, but the one way we could do it would be to simplify it to begin with. Another would be to use the quotient rule here, which we totally could. I tend to like to simplify it. So I'm not even going to do the derivative yet. I'm just going to simplify this equation. And I'm going to simplify it by multiplying by the conjugate. And I want you guys to see this because you've been using the conjugate a lot, and this is just a different way to use it using trig. You also should have done this when you were doing trig proofs last year in pre-cal, so maybe this will start to jog some of the memory there. On the bottom, you get 1 minus cos squared x. That's just a conjugate. On top, we are not multiplying this out. I feel like I've said that tons of times. The bottom is a trig identity. 1 minus cos squared is sine squared of x. Some of you might be able to see where this is going to go. This guy will cancel with 1 power, and then I have this. Now, it might not look like I've gotten very far, but in actuality I have, because unlike this guy, this I can split up. So this can be rewritten as this. And this is really cosecant. And this is really cotan. So I'm going to come back over here. This is what I'm actually going to take the derivative of, and that's way easier to do. So the derivative of y with respect to x is, well, cosecant is negative cosecant cotan minus the derivative of cotan is negative cosec squared x. So again, I'll just go ahead and clean that up a little bit. And in the future, oops, I missed an x. In the future, we're going to start factoring things that are like out. So again, this is fine for now, but just kind of start to think about, oh, I could have brought out maybe even perhaps a negative cosecant x, which would have given me cotan x minus cosecant x. This is just somewhere we're going to go when we start setting these things equal to 0 and so on and so forth. Just things to think about. Got a few more examples here. The derivative for this guy, I'm going to do this guy according to a product rule. But notice I put the parentheses. It's a lot more, I think, obvious what the product is. So product rule says I can take the derivative of the first, so that's just 2x, times the second, sine x, plus the first times the derivative of that, and you guys should know the derivative of that, we just proved it, is cos x, positive cos x. Again, that's technically it, but in the future you might want to start seeing, oh, these both have an x, I can factor an x out. Again, I do not need you to do this now, just something to start thinking about for the future. In our last couple of examples, we're doing some work with tan lines. In this first one, I want the equation of the tan line at pi over 4. I like to get the point that I'm going to use first, and that's going to be whatever I get when I plug pi over 4 into the original equation. Tan at pi over 4 is the easiest one. It's 1. Next, I need the slope. To get slope, I need derivative. So again, if you recall, I'll go back and show you. Derivative of tan is sec squared. So f prime of x equals sec squared x. And if I want the slope at pi over 4, I'm going to need to plug in pi over 4. Now, for some of you, it's been a bit since you've done some of these, and you need to know them. Secant at pi over 4 is the same as the reciprocal of cos at pi over 4, right? Cos at pi over 4 is root 2 over 2, and the reciprocal of root 2 over 2 is just root 2. So secant of pi over 4 is root 2. You can review that as many times as you need to, but that is what I end up. But because it's secant squared, it just comes out to 2. So my slope is 2. So the equation of my line that's tangent is y minus 1, slope times x minus pi over 4. Done. The equation of the normal line, well, a normal line is perpendicular. If you took RL, you would know that. If you didn't take RL, you might not know that. Normal just means perpendicular. So I'm going to go through the same point, guys. Pi over 4, 1, because that's what I'm looking at. But being normal would mean you want the slope that's not the same as the tan line, but I want the slope that's perpendicular. You guys should know from many of your maths that perpendicular is just when the slope is the opposite reciprocal of what it should be. So perpendicular would be opposite reciprocal. Then you're ready to write your equation. It's basically going to look like this. I'm just using that opposite reciprocal slope. And there we go. All right, last one gives you f of x, and they want you to find where f prime of x is equal to 0. So I guess the first thing we should do is find f prime of x. So I can take the derivative of each part, derivative of x, 1, derivative of sine, cos x. Okay, I'm going to set this equal to 0. So I'm solving this little piece right here. So that would be when cos x equals negative 1. And this is something you guys need to be able to solve. Cosine is negative 1 at pi. Technically also 3 pi and 5 pi. But I think we usually do just for that first one around. So if x is pi, it would be 0. And then again, we could keep going. The next part just wants me to write the equation of the tan line at 0. Okay. Once again, I need a point, and that's going to be what I get when I plug in 0. If I plug in 0, I get 0 plus 0. And the slope is what I get when I plug in 0. F prime of 0 ends up being 1 plus 1, so 2. And then I end up with y minus 0, 2 times x minus 0. Obviously, I could clean that up to just be y equals 2x. All right, good luck with the problem set, and I'll see you in class.